Welcome back to the Deep Dive, everybody. Today in the Science Corner, we're going really deep, down to the silicon. We're going to be talking about microcode in processor design.
Oh, this is going to be fun.
It is, right? This is the stuff that makes, for folks who love to understand how things actually work.
At the lowest level.
This is it.
The foundation, yeah.
This is the foundation of how a computer executes instructions.
Right. How the ones and zeros actually get turned into actions.
Yeah, and we're going to try to do it in a way that is, again, approachable, fun.
Absolutely.
We're assuming our listeners are smart people.
Yes, we are.
And we don't have to, rematch all the basics. But microcode.
Right.
So maybe we should just jump right into it. What is microcode? I mean, where does it fit in the whole scheme of, when I hit the letter A on my keyboard?
Right.
Or, open an app or whatever. Where is microcode?
So, like you said, we're going deep. We're going down to the silicon.
Yeah.
Your CPU, the central processing unit, that's the brain of your computer.
Yeah.
Microcode lives, essentially between the CPU hardware itself, the transistors, and the machine code.
Okay.
That programmers write. So it's this intermediary layer that translates those high-level instructions.
Oh, so it is a translation layer.
It is a translation layer.
Okay.
Because, the hardware, you hit the A key.
Right.
The hardware doesn't know what that means.
No, it doesn't speak English.
Yeah, not at all. So the machine code has to be translated into a series of very, very basic steps.
So it takes a complex instruction and it breaks it down into
Exactly.
sub-instructions.
Sub-instructions.
Okay.
And those are the microcode.
Got it.
And it has to do this because the circuits, the transistors in the CPU,
right,
they can only do very simple things.
Right.
Add, subtract, move data.
Got it. Got it.
Microcode orchestrates all of that.
I've heard the player piano analogy.
Right.
Is that a good analogy?
It's not bad. I mean, think about it. You've got the paper roll.
Right.
With the holes punched in it.
Yes.
That's kind of like the microcode.
Right.
And those holes tell the hammers.
Right.
Which strings to hit. That's the hardware.
I like that. That works for me.
Right. So the music is the result, and that's the program running.
Okay. So the microcode is telling the hardware what to do.
Exactly.
At a very granular level.
Very granular level, step by step.
Okay, and so where does this microcode live? Physically, where is it?
Right, so it's not in your RAM, the main memory.
Okay.
It's actually on the CPU chip itself.
Okay.
In a special, very fast memory.
Built into the CPU.
Built in, yeah. Because it needs to be accessed really, really quickly.
Got it.
Every time an instruction is executed.
Okay, that makes sense. So you've got this extra layer, right? I mean, you've got the machine code.
Right.
And then you've got this microcode.
Right.
Why? Why bother? Why not just have the machine code directly talk to the hardware?
Okay, so there's a few reasons. One is historical.
Okay.
In the very, very early days of computers, CPUs were hardwired.
Okay.
Meaning the control logic was basically fixed circuits.
Oh, wow.
And for very simple instructions, that was fine. It was fast.
Okay.
But as instructions got more complex, as computers evolved,
right,
this hardwiring became a nightmare.
Yeah.
I mean, imagine trying to rewire a CPU every time you wanted to add a new instruction.
Right, yeah.
So microcode came along as a way to make things more flexible.
Okay, so it's like software for the hardware.
Kind of, yeah. It's a way to program the hardware.
Okay.
And if you need to change something, you just change the microcode.
You don't have to rewire everything.
Exactly.
Yeah.
Much, much easier.
Okay, so flexibility.
Flexibility.
Got it.
That's one big reason.
And you mentioned also the complexity of instructions.
Right. So, a single machine code instruction could actually involve dozens or even hundreds of tiny little steps at the hardware level.
Mm-hmm. Right.
And microcode handles all of that.
It breaks it down.
Breaks it down.
Okay.
It's like a recipe.
Okay.
You want to bake a cake.
Right.
You don't just say bake cake.
Right. Yeah, no. There's a lot of steps.
You need to mix the ingredients, preheat the oven.
Yeah.
Microcode is like the detailed instructions.
Got it. Okay.
For the CPU.
So it's the recipe for the cake.
Exactly.
Okay, so flexibility, complexity.
Right.
What else? Why microcode?
Okay, so this is a big one, especially back in the day.
Okay.
Compatibility.
Okay.
So imagine you've got a family of computers.
Right.
Different models.
Right.
Some are cheaper, some are more powerful.
Sure.
But they all need to run the same software.
Right. You don't want to rewrite your software for every computer you buy.
Exactly. So how do you do that? Microcode.
Oh.
You can have a simpler, cheaper CPU.
Right.
That uses microcode to emulate a more powerful CPU.
Oh, so it's like faking it.
It's kind of like faking it.
Okay.
Okay.
But the software doesn't know the difference.
That's amazing.
So you get compatibility across the whole product line.
So that was a huge selling point, I imagine.
Oh, yeah, especially for companies like IBM back in the day, you know.
Right.
Their System 360, all those different models.
Right.
Same instruction set, thanks to Microcode.
So they didn't have to rewrite software for every model.
Exactly. Huge advantage.
Okay, so flexibility, complexity, compatibility.
Right.
I'm sure there's more.
Oh, yeah. What if you find a bug in the CPU?
Ooh, right, yeah. Like after it's already been manufactured.
After it's shipped.
Yeah.
You don't want to have to recall all those chips.
Right. Oh, that's a nightmare.
It's a disaster. So often you can fix these bugs with a microcode update.
Like a software patch.
Exactly. Just like a software patch.
So you're patching the hardware with software.
Pretty much, yeah.
That's amazing.
It's a lifesaver. And it's also how they address security vulnerabilities. Oh, right. Because if there's a security flaw at the hardware level...
That's a big problem.
Yeah.
So microcode updates can fix those too.
Wow. So microcode is like a secret weapon.
It's a powerful tool.
Yeah.
In the hands of the processor designers.
Okay, so we've talked about why microcode is important.
Right.
But how does it actually work? Like, how is it stored?
Okay, so traditionally, microcode was stored in ROM.
ROM, read-only memory.
Right. And sometimes in programmable logic arrays, PLAs.
Okay.
These are basically non-volatile memory chips.
Meaning?
Meaning they retain their contents even when the power is off.
Oh, okay.
And they're usually fixed at the factory.
Okay.
So once the chip is made, the microcode is set.
Got it. But you said traditionally.
Right, because nowadays, many processors use a writable control store.
Okay, writable. So you can change it.
You can change it.
Okay.
This means the microcode is stored in something like SRAM.
Okay.
Or even flash memory.
Oh, okay.
And it's loaded when the CPU boots up.
Oh, I see.
So this allows for updates, like we talked about.
Right, the microcode updates.
Exactly.
Okay, so the microcode is stored in this special memory.
Right.
And it's made up of micro-instructions.
Yes.
So what do these micro-instructions look like?
Well, there are two main types, horizontal and vertical.
Okay.
Horizontal microcode, the instructions are wider.
Wider, meaning?
Meaning they have more bits.
Okay.
Sometimes 50, sometimes over 100.
Wow.
And each bit, or group of bits, directly controls a specific part of the CPU.
So it's very direct.
Very direct, very parallel.
Okay.
So a single horizontal micro instruction might say, move data from register A to the ALU and add the contents of register B.
And all that's happening at the same time?
Potentially, yeah. It depends on the design.
Wow.
And it also might specify where to store the result.
Okay.
Update status flags, all sorts of things.
So it's like a very detailed, very specific set of instructions.
Yeah, exactly.
Okay, and then vertical microcode.
Vertical microcode is more encoded.
Encoded.
Meaning it uses fewer bits.
Okay.
So the instructions are shorter.
Right.
But this means they need to be decoded.
Decoded.
Yeah, the CPU needs to figure out what the bits actually mean.
Oh, I see. So it's like a shorthand.
Kind of, yeah.
Yeah.
It's a more compact way to represent the instructions.
Okay.
But it adds a little bit of overhead.
Because of the decoding.
Right.
Okay, so horizontal is faster, but takes up more space.
Generally, yeah.
And vertical is slower, but more compact.
Right.
Got it.
And some processors use a combination of both.
Oh, okay.
Depends on the design trade-offs.
Makes sense. So we've got this microcode, these micro instructions.
Right.
What's the history of this? Like, who came up with this idea?
Well, the very early concepts, go back to the late 40s.
Yeah.
The MIT Whirlwind computer.
All right.
It used something called a control store.
Okay.
But the term microprogramming, that came from Maurice Wilkes
Okay.
in the early 50s.
Okay.
He's considered the pioneer.
The father of microcode.
Yeah. In a way, yeah, he laid the groundwork,
Okay.
but it didn't really take off right away.
Why not?
Well, one reason was the cost of memory.
Right.
Back then, ROM was expensive.
Okay.
So it wasn't really cheaper than just hardwiring everything.
Okay, so it wasn't economically viable.
Exactly. But that changed in the 60s.
Okay.
Memory got cheaper.
Right.
And that's when microcode really took off.
Okay.
Especially with the IBM System 360.
That was a big deal. Yeah.
Huge deal. One of the first major computer architectures to use microcode extensively.
And that's what allowed them to have all those different models?
Exactly. They could use different types of memory for the microcode.
Okay.
Depending on the price and performance of the model.
Got it.
But they all ran the same software.
Thanks to microcode.
Thanks to microcode.
Okay, so IBM made it big.
Yeah, they popularized it.
Okay.
And then it spread to mini computers.
Okay.
The PDP-11, the VAX.
Right.
all used microcode.
So by the 70s, microcode was everywhere.
Pretty much, yeah. Even early microprocessors used it.
Yeah.
The Intel 8086, the Motorola 68000, they all had microcode.
So what happened? Why isn't everything microcoded today?
Well, that's a good question.
Huh?
You know, in the 80s, this new philosophy came along.
Okay.
RISC.
RISC, Reduced Instruction Set Computer.
Right.
I've heard of that.
So the idea behind RISC was to simplify the instruction set.
Okay.
Focus on the most common instructions.
Right.
And make those really, really fast.
By hardwiring them.
Exactly. No microcode for those.
Okay.
So it was a trade-off.
Right.
Simpler instructions, but faster execution.
And that worked?
It did, yeah. RISC processors started to outperform the more complex CISC processors.
Okay.
At least for certain tasks.
Okay.
So the world kind of shifted towards RISC.
Okay.
But that doesn't mean microcode went away completely.
So it's still around?
It's still around, yeah.
Yeah.
Especially in those more complex CISC processors.
Okay.
Like the x86.
The ones in our desktops and laptops?
Right. They still use microcode for the more complex instructions.
Oh, okay.
And for things like microcode updates.
Right, right.
So it's a hybrid approach.
Okay, so microcode is still relevant today.
Absolutely. It's not as widespread as it used to be.
Right.
But it's still a vital part of many processor designs.
Okay, so we've talked about the history, the reasons for microcode.
Right.
But can you give us some specific examples of systems that used microcode?
Oh, yeah, tons of examples. I mean, we've talked about the IBM System 360.
Right.
But there's also the PDP series from Digital Equipment Corporation.
Okay.
The PDP-9, the PDP-10, the PDP-11.
All microcoded?
Largely, yeah.
Wow.
And the Data General Eclipse.
Okay.
The Burroughs B700 and B1700.
Okay.
Those used really sophisticated microcode.
Wow.
Even the Xerox Alto.
Okay.
That was an early personal computer.
Right.
It used microcode.
Wow, so all sorts of different systems.
Yeah, from mainframes to mini computers to personal computer.
That'd be amazing. What about more recent examples?
Well, the Nintendo 64 used microcode in its graphics chip.
Oh, wow.
The Reality coprocessor.
Okay.
And the Sony PlayStation 2.
Okay.
Its vector units were microprogrammable.
Wow, so even game consoles.
Yeah.
Amazing.
And even today, a lot of embedded systems use microcode.
Oh.
Things like video cards, network interface controllers.
Yeah, right.
They often have patchable microcode.
For updates and bug fixes.
Exactly.
Okay, so microcode is still all around us.
It's everywhere, yeah. Just
yeah.
hidden away.
Okay, so before we wrap up, I want to talk a little bit about the implementation.
Okay.
Like, what are the key components of a microcoded CPU?
Right. So you usually have an instruction unit,
Okay.
sometimes called the I unit,
Okay.
that fetches the instructions from memory and decodes them.
Right.
Then you have the microsequencer.
Okay.
That's the control unit for the microcode.
Right.
It figures out which micro instruction to execute next.
Okay.
And, of course, you have registers.
Right.
Those hold the data. And the ALU.
The arithmetic logic unit.
Right, that does the actual calculations.
Okay.
And then you might have other units, depending on the design.
Okay.
For memory access, for input-output.
Got it.
But those are the basics.
Okay, and how is this microcode actually created?
Well, it's a specialized process.
Okay.
Microprogrammers use microassemblers
Okay.
to write the microcode.
Right.
And they use simulators
Okay.
to test it.
Okay, so it's a pretty specialized area.
Oh, yeah, definitely.
Okay, so last question.
Okay.
We talked about the trade-offs between horizontal and vertical microcode.
Right.
Can you just summarize those again?
Sure. So horizontal microcode, it's very parallel,
Okay.
but it takes up more space.
Right.
Vertical microcode is more compact,
Okay.
but it requires decoding.
Right.
So it's a little bit slower.
Okay.
And the best choice really depends on the specific processor.
Right, the design goals.
Exactly.
Okay, well, this has been incredibly fascinating.
It's a fascinating topic.
I feel like I have a much better understanding of what's actually going on.
Down in the silicon.
Yeah, down in the silicon. So for our listeners out there, the key takeaway here is that microcode is this hidden layer
Right?
that makes our computers work.
It's the translator.
Yeah, it's the translator. It takes those high-level instructions
Right.
and breaks them down into something the hardware can understand.
Exactly.
And it allows for flexibility, compatibility, updatability.
All those good things.
Yeah, all those good things. And it's still relevant today,
Absolutely.
even in the age of RISC.
Still there, behind the scenes.
So as we wrap up this deep dive, I want to leave our listeners with a thought.
Okay.
You know, processors are constantly evolving.
Right.
We've got multi-core processors.
Yeah.
We've got specialized processors for graphics, for AI.
Right.
So where does microcode fit into all of this?
Yeah, that's a great question.
How is it going to evolve?
Yeah.
What's the future of microcode?
I don't have a crystal ball. Right.
But I think it's safe to say that microcode will continue to play an important role.
Okay.
Maybe not in the same way as it did in the past.
Right.
But it will adapt.
It will evolve.
It has to.
Because the world of computing is constantly changing.
It is.
And microcode will have to change with it.
Absolutely.
Well, that's it for our deep dive into microcode.
Thanks for having me.
Thanks for joining us in the Science Corner.
It was fun.
We'll see you next time for another deep dive into the world of science and technology.
See that?
Bye, everyone.